features of neutron stars. In neutron stars, the atoms have all collapsed, the electron clouds have all been sucked in, and the whole thing becomes a single entity with the electrons running around side by side with proton, neutron in a gas or fluid. Neutron stars are made in supernova explosions, which are giant neutrino factories. A supernova radiates 10 times more than neutrino than there are particles, protons, neutrons, and electrons in the Sun.
Quasars were identified relatively recent, and our journey of understanding them has just begun. First quasars were identified in the 1950s as sources of radio wave emission of unknown origin. Quasars are astrophysical phenomena that are thought to occur in young galaxies where there is a lot of material to fuel the quasar. Basically, quasars form when supermassive black holes feed on an abundant matter such as gas or dust. This results in a massive output of energy. Quasars existed in the early age of the universe, and some exist in young galaxies that have enough material to create them. The real power behind quasars are the supermassive black holes. Subtypes of quasars. There are many subtypes of quasars that display distinct properties. Radio-loud quasars. One characteristic is their powerful jets that have strong sources of radio wavelength emission. Around 10% of the overall quasar population is made up of this subtype of a quasar. Broad absorption line BAL quasars. Their spectra exhibit broad absorption lines that are blue-shifted relative to the quasar's rest frame. Broad absorption lines are found in around 10% of quasars and are usually radio quiet. Red quasars. They are redder than normal quasars, believed to be caused by dust extinction within the quasar's host galaxy. Pulsars are spherical, compact objects that are about the size of a large city but contain more mass than the Sun. Scientists are using pulsars to study extreme states of matter, search for planets beyond Earth's solar system, and measure cosmic distances. Pulsars or neutron stars are also highly magnetic. While Earth has a magnetic field that's just strong enough to exert a gentle tug on a compass needle, pulsars have magnetic fields that range from 100 million times to 1 quadrillion, a million billion, times stronger than Earth's. Why do pulsars spin? Pulsars spin because the stars from which they formed also rotate, and the collapse of the stellar material will naturally increase the pulsar's rotation speed. The artist's impression provides an idea of how the magnetic field lines from a pulsar will loop around it and connect at the two poles. However, in reality, as the pulsar spins, it whips the magnetic field around with it, creating a much more tangled picture. In the pulsar's magnetosphere, this basic process may generate light in the optical and X-ray range. Pulsars are fantastic cosmic tools for scientists to study a wide range of phenomena. Light emitted by a pulsar carries information about these objects and what is happening inside them. That means pulsars give scientists information about the physics of neutron stars, which are the densest material in the universe with the exception of whatever happens to matter inside a black hole. All pulsars slow down gradually as they age. The radiation emitted by a pulsar is jointly powered by its magnetic field and its spin. As a result, a pulsar that slows down also loses power, and gradually stops emitting radiation, or at least, it stops emitting enough radiation for telescopes to detect. When pulsars reach this stage of life, they enter what's known as the pulsar graveyard.
Hi, I'm Jeffrey Alakain, and today I will be discussing to you about black hole. First, what is black hole? Black hole is a cosmic body of extremely intense gravity from which nothing, not even light, can escape. A black hole can be formed by the death of a massive star. One such supermassive black hole, Sagittarius A, exists at the center of the Milky Way galaxy. Observation of stars orbiting the position of Sagittarius A demonstrates the presence of a black hole with a mass equivalent to more than 4 million stars. Based from the image, we can see the structure of black holes. First, let's discuss about relativistic jet. When stars are absorbed by black holes, jets of particles and radiation are blasted out of near light speed. Next, singularity. The very center of a black hole where matter has collapsed in a region of infinite density. Photon sphere. Photons emitted from hot plasma near the black hole, which bends their trajectory producing a bright ring. Accretion disk of superheated gas and dust whirls around the black hole at immense speeds, producing electromagnetic radiation or X-rays. There are three categories of black holes. First, primordial black holes. These are the smallest of black holes and range from an atom size to a mountain mass. Next is stellar black holes. These are the most common of black holes and they can be up to 20 times more massive than the Sun. There are also a variety of all over the Milky Way. Supermassive black holes. These are the largest of black holes, being more than 1 million times more than the mass of the Sun.